Now begins a tutorial regarding how we approach acid-base equilibria problems. Zumdahl does a beautiful job really talking about what makes acid-base equilibria different. And really, to be honest and upfront, is they differ because there's often numerous things in your acidic or basic environment that you'll be asked about or you'll be given. And so we really have to approach the problems in a systematic fashion, not memorizing, just knowing the questions we should be asking ourselves and really think through every step. I love that he says, we want to approach these problems in a step-by-step fashion, letting the problem guide you. Don't fight the problem. It often will win if we let it. Okay, so Zumdahl does a good job giving us kind of a set of steps. And I've went ahead and outlined it here. If we would have a 1 molar just strong acid solution, we should be asking ourselves, okay, what do we have in greatest concentration? Well, of course, we'd have water as our solvent and then the HCl. Well, if we're trying to figure out what is responsible for producing or consuming the hydrogen ion, well, we know that this will completely ionize, and then we're going to get a little bit of the self-ionization of water. But we know that this will be so minute. Given, if we want to look at the Kw as, comparable to the Ka, we know that this is the dominant source of the hydrogen ion. And that's all that we need to figure out. What is our dominant source, or what is impacting that dominant source? And then just go from there. So let's begin with the first problem that is given within your packet. And so if you take a moment to read this, what we're being asked to find is the pH of this acid, and it's 0.1 molar. Okay, so what is our dominant species? Yeah, we have water there, but it's going to be 10 to the negative 14th in its strength, so we only need to consider the equilibria of this acid. And it is absolutely up to you if you want to write water or not in your equilibria reaction. And if we are including water, we want to write hydronium and then the conjugate base. And then we know we want to write our Ka expression right to the right. All right. Now, you absolutely can we know water is there, but you are fine. Oh my gosh. To ignore water, but we know it's there. And then your Ka would simply be your hydrogen ion, and then your hypochlorite, and then the HClO. All right, so our ice table. We're asked for pH, so I know at the end, I want to know, well, what is the equilibrium concentration of my hydronium? Water doesn't play a role in the Ka, doesn't play a role in our ice table. So for me, I'm just going to draw a squiggly line because I know that I won't insert molarities here. I don't need to keep track of anything this is doing for my Ka expression. And for my personality, if I see something empty, I think I've done something wrong or I'm missing something. So I like that squiggly. You don't have to. You could even go this route. All right. Initially, we're given this solution. And I'm just going to assume I have just made this. So it is yet to find its way to equilibria. So I don't have any of these guys. So I know to get to equilibria, I will be shifting right. So I need to find my value of X, that'll be my hydronium ion concentration at equilibria. I can then take the negative log of it to get the pH. All right, we need to find our value of X given our value of Ka. So 3.5 times 10 to the minus 8th is equal to X over 0.1 molar minus X. All right, ladies and gentlemen, this is something that we have a choice with. We can go ahead and, get X squared, multiply both sides by this quantity, distribute, find our X. We could use the solver to find our X. However, with acid-base equilibria, because there's no middle of the ground, we either have a very strong acid with crazy high Kas or a weak acid with very low Ka values. Because of the given concentration that we know we're going to be working with our weak acid, and there's the overwhelming majority of it will stay as this molecule. Per sig fig rules, when I actually find my value of X, probably it will not change this value from 0.100 at all, really. These are probably going to be, 10 to the negative fifth or something else like that. So per sig fig rules, probably at equilibrium, I'm going to end up with 0.1 molar. So it's something called the 5% rule. As long as whenever you find your value of X, it is not equal to or greater than 5% of what you are intending to subtract it or add it to, we can ignore X. That really simplifies our math, doesn't it? So let's just see. If I would ignore the subtraction of X, then I get 3.5 times 10 to the minus 8th is equal to X squared simply over 0.1 molar. Then, if I keep going, I find that my X is equal to 5.9 times 10 to the minus 5th. And I'm solving for concentration, so I know it's molarity. Now we need to check the 5% rule. So to check, we need to see if what we found for our X, 5.9 times 10 to the minus 5th molar, is 5% or greater of what we were intending to subtract it to or what we ignored it from. So if I take that, divide it out, then I get 0.059%. It definitely passes the 5% rule. So you have a choice. With weak acid, weak base equilibria, we can apply the 5% rule. We just show a squiggly line. We're ignoring the subtraction. You need to first show that you've set it up, but we squiggly through it. And then go ahead and do your math. And then all that we have to do is write 5%. And you do need to check. So you would do this math just in your calculator. You don't have to actually show it on paper. And once you have proven just on your calculator that it is lower than 5% of what you ignored it from, you just put 5%, check, and you're good. Okay, so this is our hydronium. So we're just trying to find the pH. So if you would have said, okay, my X is my hydronium, and we know pH is negative log of hydronium. Okay, you've already established this is your hydronium. Then, if you have the pH, it's understood that you inputted it there. We just can't write a pH and it just seemed to appear out of the sky. So we need to make some connection, but you don't have to write down every step. So if you take the negative log of what you just found, 5.9 times 10 to the minus 5th, remember that we want to increase sig figs by 1 when we do a logarithm. So the pH of this solution will be 4.23. And that is our final answer. So if we take a look, that introduces the 5% rule, how we would approach if you're just given an acidic solution.